A new section of the notes on laser fundamentals. So this is where we're going to actually think about the processes that happen inside the laser, how it works. So we don't just look at it as a black box with light coming out. We actually have some understanding as to the physical processes which are going on, but also the engineering bits and pieces that you might find inside the laser. So the section is broken down into two components, two sections. The first dealing with the kind of theory of the laser, how it works, and then the second section on the various components that you might find inside a typical laser. Before we think about laser radiation, we've got to think about, well, how do we generate light? How do we create light? We've looked at the ways in which light can interact with materials, but how do we actually generate that light? Well, obviously there's lots of different ways, but let's just think of the simplest way. You have a piece of material that doesn't burn, like steel, and you heat it up, and as it gets warmer and warmer and the temperature goes up and up, it starts to glow a very, very dull red colour. And as the temperature increases, then it starts to glow more of an orange colour. So you're getting the reds and the yellows being emitted. And then as we increase the temperature again, then it starts to glow white hot. And that means it's giving out reds and yellows and greens and blues. So this process of thermal production of light was fairly well understood. The basic idea was understood before the advent of quantum theory, and people like Boltzmann had a pretty good understanding of how this all worked. The special thing about laser light is that it's not a thermal process. It's a process by stimulated emission. So we'll see exactly what that means in a little while. But Max Planck described the distribution of the light with temperature for a thermal radiation. So it may be that for low temperatures you get lots of red, and then you heat it up, you get some yellows and oranges. I'm going to erase that because that's a terrible drawing. And so at low temperatures, relatively low temperatures, you might get lots of red light, and then as you heat up the piece of steel, piece of metal further, you might get more red, yellow and orangey light, and then as you heat it up even further, then you'll get more blues and greens. This is the blue end, and that's the red end. Okay, so that was fairly well understood from that distribution, the shape of that curve, the shape of this as a function of a as a dispersed spectrum was fairly well understood. Albert Einstein then took some of the ideas from quantum theory and introduced the idea of stimulated emission. So what we'll see is we'll start off with the thermal process. We'll look at the laser process, the quantum process, and then we'll see that they actually give us something which is very similar in terms of the shape of the curve, which is exactly as it should be. It should predict what we actually measure in the real world. So the key thing for laser is this idea of stimulated emission. As I say, we'll come back to that. And the word laser comes from the acronym that light amplification by the stimulated emission of radiation. Okay, so we're going to amplify the light using this process of stimulated emission. Let's think first of all, though, about black body radiation, or this thermal process. If we had, let's supposing, a lump of carbon, and we had a little cube of carbon, and we heated it up, and we put a hole in the carbon so that there's a hollow sphere inside here, and that's a cavity. Then the perfect black body would be this isothermal enclosure, and the whole thing would be in a thermal equilibrium. So that would be like a perfect black body. Okay, perfect black body gives out all wavelengths and absorbs all wavelengths to some degree or other. And we saw in my badly drawn graph above that as we go up in temperature, then the shape of that spectrum changes. So here you've got mostly infrared light. Here's the visible. At 900 Kelvin, there's no visible light at all there. Okay, it's not until we get up into the higher temperatures, so here's 1100 Kelvin, 1250, 1400, 1600, that we're starting to see sunlight coming into the visible spectrum. So the temperature is related to the shape of that curve and the total area under the curve, and also the peak of the curve, where the peak occurs. So that wavelength lambda t at lambda max times the temperature in Kelvin is equal to a constant. So for any given temperature, you can work out where the peak of the curve is going to be. So if we have one of those black body enclosures and we start to heat it up, then it will start generating electromagnetic radiation. It will start producing heat for infrared radiation. You'll be able to feel the heat before you can see any light. And that distribution of the frequencies or wavelengths depends on temperature, as we saw above. The energy distribution, or the shape of that curve, is given by this expression here. So rho of nu is the density of the radiation of the light per unit frequency. Okay, so it's the number of joules per cubic meter per hertz. H is Boltzmann's constant, H is Planck's constant, K is Boltzmann's constant, C is the speed of light. And you can see that we have a constant number here, and we have a 1 over exponential minus 1 type shape there. We have the energy of the photon, which is being generated, the electromagnetic photon, appearing both in the top and the bottom. Now, let's think about what that curve does. As the frequency goes to 0, and as the frequency tends towards infinity, then both cases give you an energy density of 0, which is what we would expect. Okay, we would expect there to be not much light away over here at infinity, and we wouldn't expect much light to be over here at low frequencies either, at 0 frequencies. So the constant factor in that equation, equation 1, we can put the constants together and call them something new. We'll call them the density of radiation modes per unit frequency interval. So now this is the number of modes of oscillation within that cavity per cubic meter per hertz. Now let's just think about that. Let's take a cross section of our cavity, so that we have our cube with the sphere inside, and this cross section here shows us that, for example, we could have a standing wave there, and we could have another standing wave there, We could have another standing wave there. And so each of these standing waves, each of these are like degrees of freedom for an oscillation inside that cavity. And the density, the number per cubic meter of these modes for each frequency in hertz is given by this number here. Okay, you don't need to worry too much about that, but we'll meet that constant again later on, and we can compare it for the classical description of the thermodynamical model to the quantum mechanical model. The total amount of blackbody radiation, so if we integrate the area under each of these curves, then the area under the curve depends on temperature, and it depends on temperature to the power of 4. So the total amount of radiation which is emitted scales very quickly with temperature. The constant of proportionality, sigma, is referred to as the Boltzmann constant, and you can see it's made up of these fundamental constants, and is a small number, watts per square centimetre per Kelvin to the 4th. The peak we've already seen goes as a constant, so the lambda times T is a constant. Lambda is usually measured in microns for this, and T is usually measured in Kelvin, and that constant is about 3000 micron kelvins. So let's think of an example. An example here, we have an object at 5200 Kelvin. It has a radiation peak then at 6.4 nanometers, let's say 555, which is right in the middle of the green. So that doesn't mean to say that if we heat something up to that temperature it will look green. It means that most of the light that's coming out will be green. Slightly less light will be in the blue. There will be light coming out in the red and the yellow and the orange and so on, but the peak of that curve will be at the green. Okay. Most materials don't actually behave like perfect blackbody radiators. Most materials will not give you that number, sigma times tau to the 4, T to the 4, in terms of the total integrated energy coming out of total integrated radiation. There will be maybe 50%, they'll give you 50% of the ideal case. In that case, what we do is we use a factor called the emissivity, and that emissivity goes between 0 and 1. And that is essentially a fudge factor. So if the emissivity was 0.5, then we'd say, okay, this is not a perfect blackbody material. We're getting 50% of the power out that we would expect to get from a perfect blackbody radiator at the same temperature. So this value sigma is a measure of how close a material is to the ideal. And I think the best that we've got so far is carbon nanotubes, things like that. Sort of nanoscale carbon is, I think, the best material that we've got in terms of getting close to the ideal black body.